Hello, and welcome to this webinar on fraud and anomaly detection using the Oracle Autonomous Database and the Oracle machine learning algorithms that come embedded in the database. My name is Charlie Berger. I'm the Senior Director of Product Management for Machine Learning, AI, and Cognitive Analytics. In the next 35 to 45 minutes or so, I'll try to give you an overview of fraud, an overview of the Autonomous Database and the Oracle machine learning algorithms that are contained inside, and I'll talk about some use cases, show some demos, and talk about some customer examples. Um, Now, I'm going to talk mostly about the algorithms as they are manifested or contained inside the Oracle Autonomous Database up on the cloud. But of course, these same algorithms are also available in the on-premise version of the database. So I'll also cover that as well. So let's get on with it. So Oracle always requires us to show the safe harbor statement that basically says that this is a general product direction. It's no real hard and fast commitment to any futures that I may address in the course of this presentation, so please keep that in mind. So the goal of this presentation is to share information on our machine learning algorithms that are embedded in the Oracle databases, as I said, both autonomous and on-premise, and databases of cloud service and so on, and how they can be easily applied to help detect anomalies and fight fraud. I'll also discuss specific use cases and explore possible machine learning approaches to tackle these difficult problems because, of course, fighting fraud and detecting anomalies is not such easy, business. It's sometimes a little bit of a challenge. If you'd like, you can follow me on Twitter at Charlie Datamind. Sometimes I post links to things, post information about different things, and sometimes just post things that sort of I find amusing or are interesting. So when I first got into this fraud business a few years ago, I'm going to say almost about 15 years ago, I was invited with another fellow, a good colleague of mine, to deliver a talk to the Boston chapter of the American Society of Fraud Examiners, I think is what they were called. And I thought, I don't really know a whole lot about fraud as a profession, as a discipline. I should do a little bit more background research. And what I found then was kind of interesting. The facts are kind of scary sometimes. Nearly 1 out of 10 Americans would commit insurance fraud if they could get away with it. 1 in 4 say it's okay to defraud insurers, and 2 out of 5 people are not very likely or not likely at all to report someone who has ripped off an insurer. 3 out of 10, 29%, wouldn't report insurance scams committed by someone they knew, and about 35% say fraud cost their companies 5 to 10% of their claim volume. More than 30% say fraud losses cost 10 to 20% of the claim volume. Now that's a little bit scary because those costs are, pushed down upon the rest of us. And fortunately, detecting fraud before the claims are paid and upgrading their analytics were mentioned most often as the insurer's main fraud fighting priorities. So one of the things I also found interesting in these reports and studies that I read back then was that they talked about certain hotbeds for crime and fraudster campaigns and such. And one of the places they mentioned was Lawrence, Massachusetts. Now, interestingly, I lived in Lawrence, Massachusetts for a couple of years, just a couple of years. And when I was there, my car was stolen, and also our apartment was robbed and ransacked. So I guess all the information was really quite true. So also when I delved into this a little bit deeper, I found that there were a lot of accepted ways, business practices, best practices, business rules for tackling fraud. And what was interesting was the certified fraud examiners almost all came from a police detective kind of background or a military background, where in some way they were some sort of a detective, a policeman of some sort. And what they had were very common sense but insightful um, rules, if you will, business rules to detect possible fraud, like unusual behavior. The perpetrator will often display unusual behavior when taken as a whole. It's a strong indicator of fraud. They may not even take a vacation or call in sick for fear of being caught. Many complaints, stale items and reconciliations for missing deposits and paperwork, excessive voids, missing documents, excessive credit memos. So a lot of sort of detailed, specific things that would raise an eyebrow of a detective who was searching for fraud. So you'd say, well, this is pretty straightforward. This seems easy to implement, right? But it really is completely based on humans, and it's a lot of work, and it's kind of hard to do this in any kind of higher volume fashion as well. So fortunately, there are technological approaches that might come to the rescue here, or at least offer some some amount of help. I don't want to say that we can solve every problem on the planet, but I think machine learning does play a role in finding anomalies and combating fraud. So what is machine learning? Machine learning is really dealing with algorithms that automatically sift through large amounts of data and help to discover hidden patterns, because if you already knew what the patterns were, then you don't need machine learning, but discover hidden patterns, discover new insights, and hopefully even make predictions. And there's a number of different kinds of categories or functions, machine learning functions. There's attribute importance, classification, regression, clustering, and so on. And each of these are typically useful for different types of problems. The first one, attribute importance, is when you're really trying to identify the most important factors. So let's say I'm trying to figure out, well, who's likely to buy a hybrid car? Well, maybe the very first factor is, have they ever purchased a hybrid car before? How many miles do they do? Are they, what's their political affinity? Are they married, single, divorced? Do they rent or own? What's their income and so? So you want to figure out what are those top variables. In the next category with classification, that means I have a bunch of examples in the past, what we call supervised learning, and I would like to predict outcomes in the future. So I have examples of people who maybe, committed a crime, bought a hybrid car, bought season tickets to the Red Sox, whatever. And I have people who did not do those things. And using all the historical data, I'd like to sift through the historical data using the machine learning, classification, supervised learning algorithms, and see if I can't find a pattern, codify that together as a quote machine learning model that I can then understand that model and apply it to new records to make intelligent predictions. If I'm doing the same sort of thing where I'm not making a classification like A, B, C, or D, I'm more predicting a numerical value, that's called regression. And in each of these cases, of course, we have a number of algorithms that support these machine learning functions inside the Oracle machine learning offering. Clustering is where we now go switch over to an unsupervised learning technique, and we're really looking for natural sub patterns or self, groups of records or people that sort of share similarities. I don't give it an objective function, or I don't give it something to look for. I say, in an unsupervised learning point of view, look for things. And where it gets a little bit more interesting is when you go into the anomaly detection, where you're really trying to find things that sort of stand out as being, dissimilar to the training population. And you can use those clustering and the anomaly detection together as combinatorial machine learning, algorithms, and put together a more sophisticated methodology. And when this is all happening inside the where your data is managed in the Oracle database, it makes it really efficient, it makes it powerful, and it makes it more easily to be automated. And the last one is something that's typically more often done in retail, where you're looking for market basket analysis. This and this were found together typically, and when they were found together, they often also were correlated with a purchase of this item, something like that. So we have, of course, support for all these different types of techniques inside the database. And I want to go through a few more concept slides. So let's say we're trying to find patterns and we have a lot of data, and we're doing, in this case, supervised learning. Okay, we're doing a classification technique up here where we have a lot of examples, and we're looking for people who are loyal customers. They come back to Toyota or Ford and they re-up and they lease another car pretty regularly, and that's what I'm looking for, people like that. And I have people who are lease churners that once they are done with their lease, they're going to turn in their car, and maybe I want to proactively approach them, figure out, hey, what's going on? Why are you doing this? And maybe try to compel them to re-up their lease with me. Now, I steal this kind of concept or borrow it from some very clever guys, Gordon Linoff and Michael Berry, with whom I used to work with years ago, and they've written some great books on machine learning and data mining. So I highly recommend that, and I'd like to always give them credit for some of these visuals. I modified this a little bit, but it's basically their concept. And so if you take just two variables, income and customer months, and you try to fit a straight line regression through this to separate the two classes between the red lease churners and the loyal customers, you can do that, but notice it doesn't do such a great job. If I add a little bit of a curvature to the equation with some quadratic or cubic terms in the model, like age squared and things like that, I maybe get a little bit better fit, pick up a few more of the blue guys down here, and you have a little bit better separation perhaps, but it's still not so good. If I unleash machine learning techniques, very sophisticated techniques that are able to do more, find more complex patterns, a decision tree would carve through this like butter and find these patterns here. So what it really does is it iterates through every possible value of customer months and income until it finds a pattern where it finds a homogeneous subsection of people. So over here, it's found segment 1 where customer months is greater than 14. So it kind of found that curve in the data right here. And it says if customer months is more than 14 and income's less than 90, and it found that sort of curve in that curve in the data, then the prediction is that you are going to be a lease churner, one of the red guys. I'm 100% confident. How? Because I've got 8 out of 8 people in the past that fit this profile did in fact lease churn from their lease. And the support means how many of the overall population. It says 8 out of 39. So there's a total of 39 guys. And so that's one example of supervised learning where I have many examples of what I'm looking for. And if you have this much fraud, then that's what you would possibly use, something like this. If you have more rare cases, it gets a little bit more challenging, and we'll talk about that. Similarly, the algorithms found another little pocket here where if customer months is greater than 7 and income's less than 175, then I'm 66% confident because 4 out of 6 of these fellows or people were a lease churner, and that represents 6 out of 39 for the overall support. So it gives me a little bit of ideas about my population. And so we're able to provide through supervised learning and lots of historical data and lots of examples that I'm able to train on for people who do something and people who don't do it, or so on. Classification techniques. I can generate insight and prediction. But what do I do when I have very few cases? I have, say, normal customers, and then I have cell phone fraud customers where I'm trying to detect that early on and avoid that. And I can't really fit a line, a straight line, or a curved line through that. And I can't so easily use the decision tree or generalized linear model or different things because there's not enough examples to train on. So what do I do here? It's a lot harder problem. So fortunately, we have some techniques that can help with that. The clustering would be one, but more specifically, I think the anomaly detection is a great algorithm. I'll talk in a minute about how that works. But before I go into that, I wanted to talk about Waldo. Okay, hopefully you remember Waldo from reading stories to your children, or maybe you read it yourself. But Waldo was this crazy character that would always appear in a vast array of many other people, a very busy picture of a beach scene or a market or someplace. And the challenge was to try and visually scan the very complex, busy picture and find the one instance of Waldo. So we're going to have a little fun here. We're going to say, can you find Waldo in 10 seconds? Okay, get ready, set, go. And there's the picture. Now I'm going to let you look at this and see if you can find Waldo. A lot of different people out there, but there's Waldo right there. So how did I find that? How did my brain find that? Well, I'm kind of looking for the little striped shirts there, right? That kind of stands out. But here's a little striped shirt over here for this person over here, and there's other people with little striped shirts. If you kind of scan this, here's some striped shirts, but they're kind of vertical. There's other striped shirts that are horizontal. Wally has this little hat right here that kind of stands out in these glasses. And so if you scan all this, it's kind of hard, but what you end up doing is you end up looking for what's different. You try to look for this little sort of pattern here. So that's what we're going to do with the machine learning algorithms. We're going to look for things that sort of stand out. And if you can do this, it has lots of applicability, right? You can use it for ATM fraud, credit card fraud, medical prescription fraud. And some of the examples I'm going to talk about for use cases and customer references are exactly these. Okay, here's one. The UK national healthcare system, where they have nationalized healthcare. They have, I think it's 65 million people in their system, and they've identified over $1 billion of potential fraud using the Oracle database technology and the Oracle machine learning algorithms and the Oracle analytics. And it's very interesting. If you Google this, you'll find this in the paper. The punchline, the reason they're showing that dentist right there is the punchline. They can't share everything, but the one story that they would share publicly, and I've presented with them a couple of 2 or 3 different times. They're great people. They do great stuff. The one story that they would share is that they found this dentist that was submitting these claims for reimbursement, and if they tabulated it all up and looked at how it sort of stood out as an outlier, if the dentist were accurate in what they had been submitting, they would have had to have been drilling 85 cavities per hour. So the dentist says, hey, I just submitted everything on the last day, and I don't know where the truth is, somewhere in between. But they have done quite a bit of analysis, and they've had quite amazing results. So I'll talk a little bit more about that in a couple of slides down the way. So how does this work? Well, I don't mean to oversimplify things, but I've always liked Sesame Street, and I've always liked Big Bird, and Big Bird has this little song that says, he sings, one of these things is not like the others. One of these things just doesn't belong. Can you tell me which thing is not like the others by the time I finish my song? And if you click on this little YouTube link down here, you can actually see Big Bird going through his little routine, and he's looking at these four bowls of bird seed, and he's trying to say, well, what one is different? And he goes through this whole very, cute analysis, and he finally decides that the bigger one is different because it's a bigger bowl. That's what's different about it. And that's what we do with machine learning. So, and using machine learning algorithms in an automated kind of way. So in machine learning, you're looking at large haystacks of data. You're trying to find the very, very rare occurrences. And you typically have lots and lots of data and very few, or in fact, even zero examples of what you're looking for. You're just looking for things that stand out, and you're looking for, 2%, 1%, who knows, very rare occurrences. You typically have many attributes, so you don't know, how to sift through this haystack of data and attributes, and so it's difficult. And when you look at any single variable, and for each record, it may look kind of okay, like this one here, X1, wherever it is, age, income, whatever these number of ATM transactions, whatever they are. It's a little bit on the high side. This one's a little bit on the high side. This one's a little bit on the more rare occurrences of whatever this categorical or varchar variable is here. And here's another one that's on the high side. And taken collectively, these many attributes may indicate anomalous. But what we're trying to do is look for what is really different. So what we're going to do is we're going to train on what we are told or what we believe to be a fairly clean, good, normal, non-fraud population. Well, in this case, we're looking at all the things taken collectively. Maybe things stand out a little bit. So we're going to take a look at this population. We're going to build a model on what we think is normal, and then we're going to apply that model either to new records, or what's most interesting is to first apply it to the same data. So I say, hey, here's all my standard, let's say, people in my insurance company. Now here's all the claims that I have, and I'd like to build a model on that. And now I'd like to apply the model to the same data, and I'd like to score them with a prediction probability of them being dissimilar to the training population. So let's say you're looking at people, and you find some people are 8 feet tall. Well, that's a little bit unusual. Some people have 10,000 checks written per month. That's a little bit unusual. I know of a tax fraud startup that was trying to build a solution using my technology, and they had this idea that the number of IP addresses that was associated with your tax submission, if it was 1, okay. If it's 10,000, well, maybe it's a robot of some sort submitting fraudulent claims. So you want to sort of sift through the data, find out what things stand out, pull them out of the training population, and then rebuild the model and try to get an ever more pure training population. So let's take this into a real example. This is actually my own personal credit card expense. It was a few years ago, and see if you can find any fraud here. I'll give you just a second to look. But what most people do is they say, "Hey, did you really go to Monaco? Is that correct? That's got to be it." No, in fact, I did go to Monaco. It was a business trip for Oracle. I had a great and wonderful time. And in fact, on my own nickel, I did go to this Monaco cafe and had a really nice meal. Also bought some wine while I was there, and just had a tremendous time. And so that's my personal, and that's not the fraud. Another one says, "Hey, gas stations. He sure is buying a lot of gas these days, or buying products at the gas station." And what's interesting in this is if you added the geospatial location of these mobile marts. Now I'm based in the Boston area, a little bit outside of Boston, but generally the Boston area. And this was in a part of Northeast Connecticut that I thought about it. I hadn't even been to that part of Northeast Connecticut for over 10 years. Just had not driven through that section of town. So that was unusual. Here's another one. $75. I go to get gas and it's always $75. Or I go to get some gas and maybe buy a newspaper and some lottery tickets, or who knows what I'm buying. I don't know, milk. And they always come up to $75. That's a little bit unusual. Here's another one that stands out. These are pairs of $75. So each of these things, they're like 1 minute apart, 2:05 to 2:06, 11:48 to 11:49. So that's kind of unusual. And then the last one, if you're really kind of using the SQL windowing functions and thinking in that way, and this is why I think I'm so excited about Oracle technical professionals being able to apply their deep SQL and analytical skills to combine that with machine learning, they can do great things. So here, if I set up a SQL windowing function to evaluate and track the amount that I was spending in restaurants and gas stations and so on, I could set up a variable that said, here's how much he typically spends, here's how much he's spending in recent, in the recent 24 hours or so, and then have a derived variable, another derived variable, what we would call an engineered feature, that says what's the ratio between those two. And if I'm doing 1-to-1, my current behavior matches my long-term behavior, that's fine. If I'm doing 100 times what my long-term behavior was, then hey, that may not be fraud, that may not be an anomaly, but it does kind of raise an eyebrow a little bit. So my point in showing this personal example is that these are the types of things you think about when you try to go tackle fraud, and a lot of this boils down to using SQL patterns, data preparation. Now we also support and integrate with R, and we will very soon be supporting and integrating with Python. So your data science teams can speak today either R or SQL. The R gets pushed down to SQL for in-database execution, and you can make callouts to R or in the future Python to do whatever you want. But the point is, there's a lot of data preparation that you oftentimes need to do, and your Oracle technical professionals are uniquely suited to help with this challenge. So when you're trying to solve a machine learning problem, there is a well-known, well-accepted approach called CRISP-DM. It's been around for nearly 20 years now. I think it's called the Cross-Reference Industry Data Mining Model, something like that. And it's nothing too complicated. It just says, think about 5 or 6 things when you tackle a problem. And the very first one it says is start with a well-defined business problem. So I always like this comment or the statement from Albert Einstein, where he says, if I had an hour to solve a problem, I'd spend the first 55 minutes thinking about the problem and the problem definition, what is the problem statement, and the last 5 minutes thinking about solutions. So I always thought this was just genius, as of course Albert was. And the question is, if he's asked to say, save the planet, is he trying to save the men, women, and children, or the men, women, and children and the animals and the fish, or just the children, or just the, what is he trying to save? And for how long does he need to save them? Does he need to save them for eternity or just for the next 5 minutes? And so the more you think about what the problem statement is, the more you narrow in on what the solutions might be. So this is, I think, one of the most important aspects about machine learning, and particularly in solving and tackling fraud and anomaly detection kind of problems. So very quickly, I want to go through a few customer successes. Here's the one I mentioned before, the UK National Healthcare System, where they've been combating healthcare fraud, and they've been doing this for, I guess, just a few years now. But I worked with them from the beginning when they got started, and they had some very smart and bright people there: Nina Monkton, Abby Hayes, Peter Barker, Phil Godfrey, and various different people that I've worked with over the years. And they have just been pouring through their data in a very disciplined way. They started up with a data lab where they had one data scientist and one part-time DBA, and it just grew. I think they're up to 10 or 12 people right now. And they just pour through the data with Exadata, with Oracle Machine Learning, with Oracle Analytics, OBIEE. I think they're moving into OAC now. But again, 1 billion Great British pounds in savings identified. 400 million is confirmed fraud. So that means they identified as, I think this is fraud. They sent it to the investigative departments, and they said, yep, that is fraud, and now it goes to the next department to try and reclaim that money back. So to try and get, and every time I talk to them or present with them, the number goes higher. So 400 million records is pretty good. Now the next one, Fiserv. So Fiserv is another great example of applying machine learning and advanced analytics to solve problems. And Fiserv was the company that sort of first really brought to my attention the real cost of the legacy way, or the traditional way that companies are forced to deal with fraud. And that is that they would, in order to do the analytics, they would have to take the data out of the database. They'd have to move it over to something else like SAS, or today it'd be Python or R or whatever, some sort of legacy system where you have to move the data to another separate dedicated analytical server. And it was taking them 3 months to run, and then most importantly, deploy the models. They were using logistic regression models from SAS. And they got that down to a month, and then they got it down to a week using our stuff, and then they got it down to a day. So when you think about how, if you're getting attacks of some sort, or you have some sort of fraud that's going on, 3 months of letting that go on is just unacceptable. So When you build the models inside the database and you apply the models inside the database, it's just sort of immediate. So that's another great example here. Turkcell, another similar example where they were looking for phone card fraud. You would have these phone cards that would have money on them, and they detect all sorts of fraudulent behavior with the phone cards, and they get that down to 4 hours now. StubHub is another one. StubHub uses actually the integration with R that we provide, among other things. They have special I guess, formulas they use that says, oh, Charlie Berger, he's trying to sell tickets on the 50-yard line for the New England Patriots. They're going back to the Super Bowl again, yay. And Charlie Berger's trying to sell these 4 tickets on the 50-yard line. Well, part of their logic, not to share all their secrets, but is, hey, has this customer ever sold anything like this before, of this value, of this these kind of tickets, Super Bowl tickets, and so on. So they've been able to do, using the in-database machine learning and the integration with R for specialized, I guess I'd say, equations or packages they've run to reduce their online fraud quite a bit. Guarantee Bank, another similar Oracle example, using a variety of the Oracle database and analytical technologies. They're doing detection of fraud at ATMs and such. Zagra Bank, also known as UniCredit Bank in Croatia, and they were using a lot of SAS, and they were able to wean their way off of SAS and push more and more of the math and the algorithms into the database using Oracle machine learning. And they also would use the callouts into R for some specialized techniques that were not among the 30 plus algorithms that we supported. So they were doing customer targeting and also fraud detection. You kind of read what they have there. And by the way, on most of these things, I think on all of them, if you click on the links down at the bottom, you'll see you'll see a copy of their presentation, the whole full details, because I co-presented with them at Oracle World, and there's a lot of more detail in each one of these things. So let's go into the more of the product details for Oracle Machine Learning. Oracle Machine Learning, it's a total family offering of the machine learning capabilities that we have here at Oracle that are largely in the database, but they also are outside the database. And some of these things we've been morphing or changing the name just a little bit to something that's a little bit more clear and a little bit more sensible. So now everything's called Oracle Machine Learning, but you may know it as Oracle Advanced Analytics or Oracle Data Mining with the SQL APIs. That's, for the most part, the core functions of the Oracle Machine Learning offering are these in-database implementations of algorithms, and they are, at their core, SQL functions. Now we expose them, and they're all fully parallelized, all scalable. They're as any other kind of function inside the database. So they're like a complex query, if you will, except the complex query is building a machine learning model that can be built and then applied all inside the database. But not everyone who's a data scientist only speaks SQL. They also oftentimes speak R or in the Python. So what we do is we integrate with those open source packages, and we wrap and expose our algorithms so you can call them through the R and, in the very near future, early 2020, Python languages. We also wrap and expose them to through the Oracle machine learning notebooks that come packaged in the autonomous databases. We wrap and we put a GUI on them through the Oracle Data Miner GUI, which is part of it's an extension of SQL Developer. We have algorithms that run outside the database in Spark and Hadoop that's called Oracle Machine Learning for Spark. And we also have something new called Oracle Machine Learning Microservices that have been supporting Oracle applications for image analysis, cognitive image analysis, cognitive text analysis, scoring, model deployment, model management. And we will also be, that's been available and used by Oracle application teams for a little bit now, but we'll also be pushing that out onto the autonomous database. So you can also use those model management and model deployment services through REST APIs and the additional cognitive image and cognitive text capabilities that come with that as well. So it's got to be a very, very interesting and rich offering. And with this powerful, with all these powerful capabilities, you can do a lot. Now, a lot of people say, hey, just show me the algorithms. What do you have? And here they are. We have 1, 2, 3, 4, 5, 7 or 8 or more classification techniques. So if you want to use a logistic regression or a random forest or a neural network, now we do have, someone will say, well, where's XGBoost? And that's another feature that's coming in the 20C release. XGBoost will be in there along with another algorithm, MSET2, which is a process monitoring kind of algorithm, largely for process monitoring, manufacturing processes, things like that, nuclear power plants, things of that sort. So the list keeps on growing, but as of today, this is what we have. We have several different clustering techniques. We have the anomaly detection, which I'll go into greater detail on. We have the regression, attribute importance, and so on. And one of the things that's kind of in the fine print here that I think is one of the most powerful things is if you have unstructured data, and I always joke that, if your marital status is entered not as a single, married, divorced, or whatever, it says it's a paragraph, or it's a document, or it's a series of tweets, or whatever. Well, the Oracle database has Oracle text inside it that tokenizes all that data and feeds us up a vector of terms, or tokens is what we would call it. And we use something called TF-IDF, term frequency inverse document frequency, to figure out, well, that particular word, like, discount. Charlie has said the word discount or expensive 5 times more than the rest of the population uses that term. So that's kind of interesting. And I'm able to digest and ingest unstructured data in that fashion. Similarly, if you have a lot of transactional data, like in the healthcare example of the UK NHS, they had, there's, I don't know, 10,000 different possible drugs. Well, you don't need to allocate 10,000 columns. You don't need to simplify it down to opioids versus painkillers versus whatever. You can say, well, Charlie Berger had, 5 of these pills, then 2 more of these pills, then 6 of these pills, and it's stored in the database in its natural form in a transactional representation. But when we bring our algorithms to the database, when we want to mine that data, that comes in as a nested table, and we'll do the aggregations on those, and we can even do clever things to say, okay, the number of opioids that Charlie has taken is 100 times more than the population average. So those are the kind of things that we're able to do when we move the algorithms to the data management platform, rather than exporting the data out to in some flattened 2D table out to some other platform. So there's quite a bit of functionality here, and my hope is that some of these algorithms, and maybe in combination, can help you tackle some of your fraud and anomaly detection challenges. We also have quite a few statistical functions for descriptive statistics, median, standard deviation, and so on. We have t-test, f-test. A lot of people don't know that we have these things, like Pearson's correlations, Spearman's, and so on, because they've been in the database since 10GR2, and they've always just been free. So unless you read the documentation, or unless your salesperson may or may not have mentioned this to you, but there's been a lot of functionality that's been in there for quite a period of time, in addition to all the machine learning algorithms that now come with the autonomous database. So how do you use these things? Well, at their core, they're really just exposed to SQL functions. So I always like to start out with this basic statistical query here that says, I'm going to compare the average purchases that men make versus women, but I'm also going to do it with a group by. So a little bit of simple SQL to go off and do that, but now I can do a statistical t-test. And if you remember from your stats classes, any p-value less than 0.05 means it is statistically significantly different. So you can see some of the values here, 0.0396, that the amount that men buy 105 versus women is statistically significantly different when the income level is below 30,000. And on some other ones, like this one here, it's not quite as significantly different, and so on. But now I'm doing the kind of things that I might have thought that I had to, require exporting the data out to SAS, SPSS, Python, R. Now I'm doing that inside the database. Now, some people might want to use this as data preparation for fraud detection, right? I want to flag anything that's outside 3 sigma or whatever. And you can do that. The algorithms would do a lot of that sort of automatically for you as well. But sometimes you will want to explicitly generate some engineered features using techniques like this, or just perform a simple statistical descriptive statistical summary or something. When you want to build a model, it's very straightforward syntax. It's for the SQL people. I'll show the R and the Python in a second. But for SQL people, it's just begin DBMS data mining, create a model. The name of the model is by insurance. The type of function is going to be classification. The data table name is customer insurance lifetime value. The unique identifier is customer ID. The target column name here, because I'm doing supervised learning, I'm trying to find people who buy insurance, people who don't buy insurance. So the target field is buy insurance. And the settings table, like am I doing a linear regression or a quadratic, or am I doing a support vector machine that's a Gaussian kernel, or all the different sort of algorithm settings are in this algorithm settings table, and I refer to that. And so I just build the model. It should happen in 1, 2, 3, 5 seconds, maybe 20 seconds, maybe if you have a huge amount of data, maybe 10 minutes, but it's just running as a complex query inside the database. And when it's done, it's codified all those relationships up as a model, the buy insurance model, and now I can apply that model either in real time, as I'm showing here, using from dual with these values, maybe coming off my ATM machine or whatever. I'm trying to say, well, here's what's coming off the wire, make a prediction, and there it is, 93% likelihood that this is someone's going to buy insurance or commit a crime or do fraud or whatever I'm trying to do. And that's the way it works. If I'm trying to do something kind of related and similar, we talked about this earlier, the attribute importance, and I'm just saying, no, what I want to know is what are the key attributes? So I'm not really building a model so much, well, I guess I am building a model, but I'm not applying the model. I'm just saying, show me the key variables here. And here are the key variables, bank funds, 0.2161, and so on. So this is this, very same kind of syntax to do that all in SQL. So what if I don't speak SQL so much? My preferred language is R. Well, as I said, we wrap and expose and integrate with open source R. So now I can come in speaking the R language. It's going to call those same Oracle R Enterprise, Oracle Data Mining Attribute Importance function. It's going to make a call to that same function that I did before. And notice I get the exact same results. So now I'm not moving the data out to R. I want to be very clear about that. You can do that as well, and that's what we call embedded R callouts. But in those cases, you pay a price, right? You're moving the data out of the database over to an open source R, or as I said a few times, in the very near future, open source Python, and you're calling any, out in the wild R or Python package. But in those cases, you do pay a little bit of a price because you're moving the data. You're using a single threaded R package or Python package, and then returning the results. Now you can store the scripts and manage and leave them in the database and such, which is great. But maybe what you want to do is use that when you need to for some, functionality that's not explicitly supported in the database. But if you can use one of our, random forest decision trees, XGBoost or whatever, using R syntax and do all that processing inside the database, that's where you're going to get the real gain. And as I said, if you're speaking Python, if that's your native tongue, which these days a lot of people are speaking Python, well, that's very straightforward. You use the Python syntax to call the same function. You get the exact same results, 0.2161, 0.148, and so on. And you can also do the callouts to Python, use the Python graphing capabilities, and so on. So it's a multilingual kind of offering from Oracle these days. And with all this horsepower and multilingual and multi-user interfaces, we think we have a pretty interesting platform for tackling complex problems like fraud and anomaly detection. So that I'm trying to show that here. I have the notebooks that come in the autonomous databases. I have the drag and drop GUI that comes with the SQL developer. That's called Oracle Data Miner. If I'm using R, I may want to use something like RStudio, and I might use Rodeo or something else for Python. So my sort of R and Python data science can use their IDEs of their choice. Notebook users and Oracle, anyone, I suppose. The notebooks will be multilingual. So when we support R and we support Python, the notebooks on the autonomous database will have, you'll just say in the paragraph %R or %Python. Right now you say %SQL, and that paragraph is then speaking SQL. So in each paragraph, you can kind of change the language. That's the nice thing about the notebook. So teams of people can, in a collaborative environment, tackle problems. You're doing all this by leaving the data and doing all the processing as best you can inside the Oracle databases. And then the nice thing is, if you've done all that, it makes developing applications so much easier, and that's where the real power comes into play. So now with Oracle, what we're trying to do is both manage and more analyze all your data with this multi API, multi touch point, multi user kind of point of view for the algorithms. And you can do the data, leave the data in the database. But as I said before, we also have algorithms that run outside of the database. I personally think that sometimes this is a little bit oversold in terms of, do I really need to do all the analysis outside the database? Because I always think, well, do you have their age? Is that stored outside the database? Do you have their gender? Do you have when did they make their last payment? A lot of the data that you think is important is also in the database, and that data is oftentimes important for solving, business problems. And the data that's out here is also very important, but it's oftentimes in a more raw form, right? It's like the temperature gauges or the tweets or whatever. And what I want to do is boil that data down, boil down the data lake to get counts, totals, changes over times, mins, maxes, things like that. Cleverly derived engineered features that I join to the rest of the table here. And as I always say, if the centroid of this data is anywhere close to the database, I would continue forward doing all the rest of the processing inside the database, because that's where we have probably the richest and most differentiated functionality. So I just want to show a little bit of the power of what is possible now by moving all the algorithms into the database. And imagine trying to figure out, bad rental car drivers that, I'm not going to call it fraud, but I'm going to call them anomalous rental car drivers. I don't want to rent a Charlie Burger because he's not doing good things with my car when he rents it. And so I might have geospatial data out there that is stored and managed in the database, perhaps using Oracle Spatial. And maybe I want to do is figure out what % time does he spend in the city, out of the city? Is he driving through parts of Boston that has a lot of potholes? So it's very interesting to pull into the spatial data. I might have graph data where I have transactional data, relationships with how many interactions has Charlie Berger had with 2 degrees of seven, you know 7 degrees of Kevin Bacon. I've had 5 interactions with people on a suspect list or on a bad list, or who am I hanging out with basically. Once I join all that data together, I have a 360-degree view of the customer, so I can get a much better, more expansive view. I don't have to kind of simplify things. I can build many different models for risky car rental drivers, using all the algorithms and the techniques I showed, and then I can apply it to new rental car drivers, either in batch or in real time, and say, hey, what are you doing driving my rental cars through the city like that and dealing with bad people or whatever? I don't want to rent you any of my cars anymore. So it just shows you the sort of power of the art of the possible when you bring the algorithms to the data management platform. And here's a great study done by Fern Halper. I thought she asked the right question. How long does it take to put a defined model? What does that mean? It means I already built the model. So once I've built the model, which is what everyone usually talks about, hey, I used machine learning, I built this model. But more interesting is, okay, you built the model. What'd you do with it? Did you ever operationalize it? And if you look at her study, something like 65% of the population is 3 months to never, right? Which means, and then this corroborates or corresponds with another study I saw, that 87% of big data science projects fail to go into production. They're just like data science experiments. They never really go into production. And interestingly, if you remember way back to the Netflix story many years ago, where they offered $1 million to find a predictive model that was better at recommending movies to people, 10% better was the goal, they would give you $1 million. Well, no one could achieve quite the 10%. I think they got to 8.5 or 9% better, but they awarded the prize regardless to this team of people, and it made the press, and they gave out the Netflix prize and so on. Well, what nobody ever really talked about, the people from Fiserv actually were the ones that brought to my attention. They said, hey, they went back, and you know what? They never actually implemented that better methodology. Why? Because of this slide here. It was just too hard to do. How do you, once I've built that model that has all these coefficients and all these terms, and it's done in Python or R or whatever, how do I operationalize that? And I have to oftentimes manually recode, rewrite the logic. I can't just run it as a SQL function inside the database, or call it from R or Python and it executes as a SQL function inside the database, or a call out the way we do it. I have to use sort of these legacy systems. So this is Fern's slide. This is now my editorial comment. Well, they must be using packages and products like that, because if they were using ours, it would just be immediate, right? I just build the model, I apply the model, and I'm done. So again, Fern's slide is without the editorial comment, but that's my inference from this. So let's take a little bit more of a deeper dive into how we might approach detecting possible fraud. We're going to start with the Oracle Autonomous Database that comes with the Oracle Machine Learning. So you have the database. You could use SQL Developer. You could use OAC, Oracle Analytics Cloud, to look at the data. But we have all these cool algorithms, 30 plus algorithms that are multifunctional. They can do a lot of cool things. And we have this nice notebook that comes with the Autonomous Database. So I just open up my browser. I launch a notebook, and I'm starting to look at my data, visualize it, graph it. I'm doing an attribute importance right here. You can just see the little syntax like I showed on the previous slide. So Oracle Machine Learning, it's a collaborative user interface for data scientists. It's packaged with the Autonomous Database, and it has currently support for the SQL machine learning algorithms, and it also supports the deployment at the analytics, because I can take these notebooks and sort of execute them, and I can sort of operationalize things. There's more functionality coming from us in this space with those microservices as well. But let's take a deeper dive into this. The algorithms are the same as I showed in the earlier slide, with the exception of you don't see the Python and the R integration here yet, because that is still a little bit of roadmap. That'll be coming, as I said, in 2020, first with the Python integration, then following that with the R integration. But it's the same at the core, the SQL algorithms. You just can't call the SQL algorithms using the R or the Python syntax yet, but that is coming. So we have the full arsenal of machine learning algorithms at our disposal. And what's nice about the Oracle Machine Learning and the Autonomous Database is it comes with some demo data, and it comes with some example notebook templates. So I might want to go do the anomaly detection or the association rules, and each of these notebooks will open up a notebook that I can run the demo data and see what's going on. And they're very sort of detailed, they have very detailed explanations. So they're very, very good learning mechanisms. and I can repurpose some of these to apply them to my own data. So let's take a look at what I've done here. I've taken the anomaly detection template and I've sort of repurposed it a little bit and made some tweaks. And I now use it for this automobile insurance claims problem. So I put some of the comments about nearly 1 out of 10 Americans would commit fraud. I have a nice little sort of report here, or analysis that I'm doing. I have a nice little graphic that I can use. I can use markdown language over here. I can use insert an image over here, a little bit more markdown language over here with some links to things. And then I say, well, I would like to display the data. So that's just %SQL. So this paragraph is going to say %SQL. I have a select star from the claims data table. If I want to run that, I click run right there on the finished thing. It shows me the table. And then once I do that, what I may decide that I want to do is to graph some of that. So there are some very simple and basic graphing capabilities for doing histograms, pie charts, area plots, scatter plots, and line plots. Nothing overly sophisticated if you're trying to do a lot of interactive graphing and some really cool stuff. Of course, Oracle Analytics Cloud is great for that, and other products are great for that. Here, what we're trying to do is leave the data in place, visually explore the data a little bit, and then dive into some more deeper analysis using the algorithms. So here we find that on Fridays and Mondays, we have a few more accidents than on the other days, and we're kind of visualizing this data a little bit more. Here's some, where do the accidents happen? They happen mostly in urban areas. Some of them are in rural areas. I see the age of the policy holder versus the vehicle price. I'm kind of sifting through the data, looking at various different graphics. But if it were this easy to solve crime or fight fraud with just a bunch of pie charts and bar charts, then we wouldn't have so much crime, but it's not so easily done. What's happening then when I want to eventually go into applying the algorithms, at least in this version of the notebooks, which does not have a click, click, click sort of user interface, that's coming in something we call AutoML user interface, which is just going to be a wizards-driven click, 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 and that will also be an early 2020 new feature. But under the hood, under all these GUIs, the Oracle Data Miner or whatever, is code, right? So I put a button on something that has a bunch of code, and here's the code. So here we're going to drop the previous models, drop the previous model settings, drop the previous models. Here we're going to create a build settings. It's going to say I'm going to do a support vector machine. I'm going to do auto data preparation on, and so on. And there's my settings table. Here's where I actually build the one class support vector machine model right here. And so when I run that and I just press go, it runs through it very quickly. It builds the model in about 5 or 6 seconds, I think, on my laptop on 20,000 records, something like that. So it's very, very trivial. But even on the bigger systems, the assumption is you have a properly sized data warehouse and Exadata box or whatever. So if you have lots of data and you're building machine learning models, it's going to similarly run, through that with 512 degrees of parallelism or whatever you have, and it's going to be, lightning fast there as well. Once I've built my model, I can display all the customers in their probability of being anomalous in descending order. So I now have said, let's score this model on all these different customers and let's see what they look like. Who are these people? So if I score these in sort on probability of fraud, I see this woman, a female woman, and if I look through this, she's the #1 most suspicious claim. And if I scroll over more and more, you'll see that she has a Honda Accord, no witnesses present. I forget what day of the week it was done. But I think the most interesting discovery, from my point of view, is that she had a Honda Accord that she claimed, or in the data it said it was more than $69,000 in value, the price of the car, and that's a Honda Accord. I don't know of any Honda Accords that high. So it may be a combination of several things, but the machine learning anomaly detection algorithm, in an unsupervised learning kind of way, sifted through all the data, found what was normal, applied that to the records, and we sort in what the algorithm thinks are sort of different in a multi-peculiar kind of way. So then we can kind of sift through this data and sift through it through, maybe by their age, by display customers and probability of being anomalous, various different ways to kind of, visualize the data. And at a certain point, here are the different types of, one vehicle accident to two vehicle accident or so on. So I say that they have maybe a certain probability of being fraudulent threshold I may want to graph. So once I go through this and have all my prediction probabilities and such, I may want to stop, or I may just want to leave the data right there in the database and continue on and investigate that using something like Oracle Analytics Cloud, where I'm now sifting through the findings and the discovery. Interesting. So now I'm going to go on and talk a little bit more about the Oracle Data Miner SQL developer extension, and go through a little bit more on that. So here I have a different, I'm pivoting a little bit, a slightly different scenario. I have tax fraud. So in tax fraud, I have sort of two different ways I'm going to approach this. One is where I don't have any idea of tax fraud. I don't have any examples, so I'm going to use the unsupervised learning to build on normal or compliant tax submissions, and where I have, I'm going to think less than 2% of the training population is fraudulent, and that's what I'm trying to really discover, these needles in the haystack. And the other approach that I'm going to take is where I have the assumption that I have actually a lot of labeled data, and I say, yep, this is non-compliant, this is non-compliant, and I have a lot of examples. And I think in the data I actually have a flag that says non-compliant, yes, no, or could be. And depending on how much significance I put on that, I can really treat that as just an input variable, or I can use that as the target field. So we're going to go through this in a little bit greater detail. In the drag and drop user interface, which I'll go into a little greater detail, we have the claims data, we build an anomaly detection model, then we apply it. It's that simple. We have the probability of it being anomalous and the variables and the values for those variables as they are influencing the model to make its prediction. So it's really pretty straightforward. And let's go through a quick little drag and drop version of this. So I have my data, I've brought over my data source over to here. I click on that, I want to view the data, and there's my data. I have tax person ID, is it compliant, yes or no? So sometimes I take this as an opinion, and sometimes I take this as fact, depending on whether I'm doing supervised or unsupervised approaches. I have their salary, their marital status, their number of tax credits, deductions, and so on. So a bunch of relevant data for possibly determining whether this is a compliant tax submission or not. I then drag and drop an Explorer node over here, right mouse click on that, connect it to that, and now I see the data. And when I see the data, I'm calculating min, max, standard deviations, all of the statistics using those statistical functions I showed earlier on, and I can see the distribution of the adjusted tax income grouped by marital status. So I can kind of visualize my data to see if it makes sense, is what I'm typically trying to do here in a machine learning point of view. I can then go off a little bit deeper and do some filter columns. Why would I do this? I want to see, well, some of these columns that I'm feeding in, if I'm bringing the algorithms to the database and I'm sifting through all this data, well, maybe some of the data is just, all constants, or it's all missing. And I also maybe want to discover, here's the number of ones that are all constants, they're all missing, or the number of unique values, like a phone number. It wouldn't really be a good input variable to a predictive model. You wouldn't want to say, well, you have this phone number, so therefore you're fraudulent. That's a little bit of overtraining a model. But I also want to do this attribute importance that says, given the target field of, in this case, supervised learning, did we flag you as being non-compliant or not? What are the variables that are most associated with that? So that's called the attribute importance. I just want to show how easy it is to do this. Now, we're going to continue on, and we're just going to let all the data flow through here. Now we're going to build an anomaly detection model, and we've done the one class support vector machine, which is what I showed before. The anomalous records, the ones that are predicting are 0, that's anomalous, 1 is normal, and here is the model. If car ownership is 1, if compliant says no, I don't think it's compliant, if the gender is male, and so on. These are all the different values these are the pieces of evidence that lead me to believe that this guy or this record is perhaps fraudulent. I go a little bit further, I can now take a new set of data, new tax submissions, take the output of that model and apply it to this new set of data and make predictions. This is all happening inside the database. This is just a script that I'm running. The models themselves are SQL functions, and I can apply it. And here are the records. They are sorted by they are here with the probability of them being suspicious. And if I click on any particular record, I can see the reasons why the algorithm has flagged this as being potentially suspicious. It says the monthly overdrawn was minus 123, and that struck me as unusual. The marital status was widowed, that struck me as unusual. It's from North Carolina, and so on. So these are the fields that for each record, what we call prediction details, where we try to explain the model's logic for making that particular prediction about that particular record. So it's pretty powerful stuff. You can do this both in the autonomous cloud or on premise using the different ways that I've shown that before. Continuing on with the Oracle data miner approach, now I'm going to shift over here and I'm going to say, well, now I'm doing classification problems. I'm going to say I have a lot of examples that were previously flagged as being fraudulent or not fraudulent. So this is not compliant, as I guess the terminology the IRS uses. So in this case, I'm doing a supervised learning kind of technique. So I'm going to look at those results. Here's a decision tree, which a lot of people like because it's very visual and it kind of explains, okay, here's a pocket of people, node 29, where if the itemized deduction is greater than 246, the adjusted um, deductions is greater than 282, and so on, then I'm going to predict that this is, no, not fraudulent, and I'm 56% confident, which actually the converse of that is I'm 44% suspicious that it is non-compliant, right? So it doesn't have to be a binary kind of thing. It could be, hey, you're 10% likely to be a criminal. Let's pull you over, you know. So you can do whatever you want here, and the support means what percentage of the population is it. So I can also generate the code behind the scenes. As I said, all of the GUIs are doing, they're just calling code, and we publish that code so you can go straight towards operationalizing or deploying things. There's also APIs that you can call. There's a variety of different ways that Oracle supports the development of applications. But what you're running under the hood is really as simple as this. You're setting up the settings table. You're dropping in a previous one. You're populating the new values with auto data preparation on. You're begin DBMS data mining create model. The target field is null, right? Why? Because I'm doing unsupervised learning. I don't have a target field, so I say none. And then once I've built it, I can apply it. There's my results right here. That script on my laptop runs in about a second or two. Your mileage may vary, but I mean, even if you have lots and lots of data, you're gonna have a much better experience just doing all the processing for the data processing and the data and the machine learning inside the database than schlepping all the data out to some other open source or SAS or R or SPSS or some other, you know, dedicated analytical platform. It's a lot better when your data management platform is a hybrid or combined data management, secure, scalable, and analytical platform all at the same time. And that's what we've done. So kind of reaching a little bit towards the end here, I just want to kind of go into some more complexities of how you might approach this. I've been mostly talking about using the anomaly detection, the one class support vector machine, to flag things that are suspicious. And what I might want to do is add a feedback loop to purify the input training data over time. So as I flag things and say, hey, I think this is suspicious, I think this is suspicious, if they are suspicious, and I confirm that, yep, that's non-compliance or that's fraud or whatever, remove them from the training population and keep on going. If I have, and you can just keep on getting better and better. As you build up more and more examples, let's say you have a lot of, maybe you have 10, 20, 25% examples of what I'm looking for, either from that, you know, setting things aside or just in general. Like I know a guy who was doing check fraud and he said, they're not anomalous. I have a lot of check fraud. So if you have a lot of examples, then you might use classification techniques where you build a model to train on separating out the fraudulent from the non-fraudulent. And that's a sort of a very similar, but a different, conceptually different approach to do things. A lot of people would also use clustering. They'll say, well, in an unsupervised learning point of view, I want to take the larger population and put them into more homogeneous subpopulations without any kind of direction from the data scientist, just from the algorithm. Just say, put all these records in sort of groupings that are sort of similar. And then what I'm going to do is I'm going to look through each record in those groupings. I'm going to say, what are the things that are not very close to the centroid? They're out near the edges. You know, like Charlie's not really a hockey dad. He's not really a soccer mom. What is he? He's a little bit in between somewhere, right? Now I could do a hybrid of 3 and 1. I could do the clustering, put you into different homogeneous subpopulations, and then for each of those subpopulations, run separate anomaly detection. Now imagine detection models. Imagine I'm doing medical fraud and I'm doing surgical procedures, but then within the surgical procedures, you know, I have orthopedic, I have plastic surgery, maybe even just in plastic surgery, I have, you know, people that do, you know, simple, I don't know, nip and tuck kind of things, and people that do sort of more complex things, and maybe people that do really expensive things in Los Angeles or whatever. For each of these different sort of subpopulations, I can have a separate anomaly detection for that. So you're getting a little bit more refined, right? And you're able to take on these more complicated ways of doing things because you have all this, you know, complexity and horsepower all, you know, neatly assembled into your same data management platform. And the last one is, why not just do all of the above, right? It's very fast and efficient to do these analyses. So let's just say, well, 3 out of 5 of the models predict that you are anomalous, more than 40% or whatever. And I'll just set up a panel of experts, another approach that people do. So visually, I want to show the difference between, here's the nice simple model, just build an anomaly detection model, and there's my suspicious claims. using the graphical user interface, you can also do this, of course, through the scripts, but using the GUI, here's the clustering model, assign everyone to their own specific clusters, and then for cluster A, cluster B, cluster C, run their own, separate anomaly detection model. So you can do a lot of different combinatorial things here. I always like to highlight this concept of engineered features because everyone talks about it being the algorithms. It's the algorithm, but it's so much more than the algorithm. And this is where I think for Oracle professionals, it's so powerful. You know SQL, you know all the SQL capabilities, and you know your domain. What you may be growing into is how to apply these algorithms as well, because they're now part of your toolkit, right? You can do all these things. So maybe what you want to do, as I said before, use the lead and lag functions to change inter-row references using offsets to say, well, how has Charlie's usage of his international phone calls gone up or down over time? What's my relative rank versus peers? In certain states, this drug is the most popular drug, but in other states, it's this drug that's the most popular drug. Those are all interesting inputs to feed into your algorithms. Reporting aggregates and comparisons, like the number of opioids that Charlie gets versus the population average. Statistical aggregates for correlations and so on. SQL windowing functions. I think I talked about that before. The average, the mid, the max amount of checks written over the past 6 months compared to the most recent 24 hours. That's a pretty interesting set of engineered features to feed into your check fraud model. And of course, there's SQL patterns, which was developed for some telco companies to kind of figure out, I call you, you call me back, and it's all going back and forth within a very short period of time. Maybe that indicates a dropped call, and I could use SQL patterns to detect these dropped calls, count the number of dropped calls, and see if they are changing over time. These are all interesting, more cleverly derived engineered features, and all of that processing is happening using the power, the scalability, the security, and the analytical power of the database. And here's just an example of that SQL patterns for calling, dropped calls or spikes or whatever we're looking for there. It's a very, very, very powerful feature if you're not aware of it. I just wanted to call that to your attention because it can come in handy for certainly finding complex things, difficult to find things like anomalies and fraud. And then when you're done, remember that decision tree that we showed before, which was something I would never ever show to the boss, right? I would say that's way too complicated. The boss just wants answers. So rather than showing something as complicated as this, which, hey, look, boss, here's all these different decision tree, um, no, groups of people, profiles of different people, and here's what the description is. Wouldn't it make a lot more sense to leave the data in the database, in the autonomous database, or the enterprise edition of the database, whatever you're using, and just call up something like Oracle Data Vision Desktop or Oracle Analytics Cloud, and that attribute importance that I showed before, well, that's a much prettier, much better graphic. I've just pointed to the results. I've done all the hard, analytical work inside the database, done all the processing there, and now I just want to surface those results using better visualization techniques than what we provide with the, machine learning tool by itself. So here's that decision tree, and if I want to see, well, who are these members of each of these different profiles? Well, it's just a drill down into the pie slice, and it seems like a much, much better way to expose and surface the results. And of course, you can take this even further and build whole applications, and that's what more and more of Oracle applications have been using them, embedded machine learning algorithms for that. For more information, I encourage you to just Google Oracle Machine Learning on OTN. You'll come to this page, which has many, many links off to other resources and documentation, demos, customer references, and so on. Getting started, training materials, and so on. So just please start out there. I also want to encourage everyone to mark their calendars and hope to join us. Hope you can join us out February 25, 26, and 27 in 2020 out in Santa Clara, California is where we're going to be this year because they're doing renovations and remodeling on the Oracle Conference Center. So please join us out there. We'll have about 500 people, hopefully, or more. All people, Oracle customers, Oracle technical professionals, Oracle experts sharing their experiences, their knowledge, and their use cases in novel and interesting use cases for analytics and data. So please join us there. Also make note of the tech cast that we have up here. It's every 2 weeks we have a tech cast. Those are all recorded, and you can watch those on demand. So it's a great and wonderful resource for you to a really nice community. It's not, and it's only like $500 to go, or even cheaper. I don't even know if you get an early bird discount, but it's kind of like a mini Oracle world, but just for analytics and data use cases. We work with OAC, Spatial and Graph, OBIEE, the database, cloud, IoT, all the different sort of technologies from Oracle that are in this applications that embedded. It's a very interesting gathering of people. So I hope you can join us. Um, Thank you very much for your time and attention in watching this webinar. Please tell your friends, anybody else that wants to watch this, and share the information, and give me any feedback if you have any at charlie.berger@oracle.com. Or of course you can follow me on Twitter at charliedatamine. Once again, thank you for your time and attention, and I wish you all the best using our Oracle machine learning algorithms. Take care.